Right now, if you look at the landscape of artificial intelligence, it feels like there is this massive, insurmountable arms race happening.
Oh, absolutely.
I mean, you have these massive tech giants throwing literally millions of dollars, mountains of data, and these incredibly complex reinforcement learning algorithms at AI models. And it's all to make them sort of think and reason.
Right, like trying to emulate human logic.
Exactly. You hear constantly about models like OpenAI's o1, which can seemingly pause, reflect, and solve these hyper-complex math or logic problems. But there's a massive catch for the rest of us.
Yeah, the budget.
Right. That methodology is locked securely behind closed doors. It requires a computing budget that really only a tech monopoly can afford. It feels like the cutting edge of AI is just moving further and further out of reach for anyone who isn't, a billionaire CEO.
It's true. There really is a widespread assumption across the industry that achieving elite human-level reasoning requires an equally elite astronomical amount of compute power during the training phase. We naturally assume that brute force is the only way forward.
But that is exactly what we are challenging today. The mission for this deep dive is to explore a fascinating new research paper titled S1, Simple Test Time Scaling.
It's a great paper.
It really is. It details how a group of researchers took a publicly available open source model, and they achieved that exact same elite O1 level reasoning capability.
Which is huge on its own.
Yeah, but here's the kicker. They did it using a shockingly simple, highly efficient method centered around how the model scales its thinking time. We are going to extract the exact recipe for this efficiency so you listening can understand the absolute cutting edge of AI.
And you won't even need a PhD in computer science to get it.
Okay, let's unpack this, because I'll be honest, it sounds almost too good to be true. How do you get a model to reason like the big tech giants without spending millions of dollars?
Well, the real magic here isn't about brute force at all. It's about surgical precision. It's about giving a model a tiny, perfect set of examples to look at and then intelligently managing its budget of time when it's actually solving a problem for you.
A budget of time.
Okay. Right. That second part, controlling how long and how effectively a model thinks when you hand it a prompt, is what we call test time scaling. And the researchers prove that test time scaling can be done with shocking efficiency.
But before we can even talk about scaling a model's thinking time, the test time scaling part, we really have to understand how this model, which they named S132B, was trained so efficiently in the first place.
Oh, the cost difference in their training method is truly mind-blowing. Building S132B started with an existing, off-the-shelf open source model.
Basically a model anyone could download.
Exactly. Specifically, one called Qwen 2.532B Instruct. This means it's freely available code, not a corporate secret. The researchers took this base model and fine-tuned it on just 1,000 carefully curated examples.
Just 1,000.
Just 1,000. They called this tiny data set S1K. And the training process took a mere 26 minutes using 16 H100 GPUs.
Wait, I need to pause on that for a second to put that into perspective for H100 GPUs are those absolute top-tier, insanely expensive microchips that power modern AI data centers.
The ones everyone is fighting over.
Exactly. Usually, companies use thousands of them for months. If you or I tried to rent 16 of those chips on a cloud server today for just 26 minutes, it would cost us less than a nice dinner out. We're talking under $50 to train an elite-level AI.
It's wild.
But wait, I have to push back on this concept. Isn't the golden rule of AI that more data is always better? You want a smarter model, you feed it the entire internet.
That's the conventional wisdom, yeah.
Right. What you're describing sounds like studying for a massive, multi-subject final exam by ignoring the entire library and just reading the 10 most relevant pages. How can 1,000 examples possibly compete with models trained on millions of reasoning paths?
What's fascinating here is a concept known as the superficial alignment hypothesis. This idea actually originated in earlier research that it perfectly explains what's happening under the hood of S132B.
Okay, lay it on me.
You have to remember, the base model they started with, Qwen 2.5, was already pre-trained on trillions of tokens. And tokens are basically the word fragments and code snippets AI uses to process language.
Right, the building blocks.
Exactly. During that massive initial pre-training phase, it already read the library. It already learned the fundamental logic, the math, the science. That deep knowledge is already baked into its neural pathways.
Oh, I see. So the 1,000 examples in this new training phase aren't teaching the model how to do math or science from scratch.
No, they aren't injecting new knowledge at all. They are acting as a behavioral key. This is why it's called superficial alignment. We are only aligning the surface-level behavior.
So it's basically just waking it up.
Precisely. The 1,000 examples simply unlock or activate the reasoning behavior that is already lying dormant inside the model. It's showing the model the specific format of how to lay out its thoughts step by step.
That makes so much sense.
And to your point about more data being better, the researchers actually tested that exact theory. They tried training the model on a much larger data set of 59,000 samples. That took 394 GPU hours compared to their 7-hour method.
And the result?
The performance gain was practically zero. Stuffing more examples into it didn't offer any substantial advantage because the model already knew the material. It just needed the 1,000 example key to know how to show its work.
That is incredible. It's like taking a brilliant but disorganized scientist and just handing them a standardized form to fill out. Once they see the format, they can pour all their existing genius into it.
That's a really good way to look at it.
But that brings up a huge logistical problem. If you only get 1,000 examples to unlock this hidden potential, clean data doesn't necessarily mean useful data.
Right.
I mean, you could have a perfectly formatted, crystal clear example of someone solving 2 plus 2, but that's not going to teach an AI to think deeply. How on earth did the researchers filter a massive pool of 59,000 questions down to the 1,000 perfectly challenging ones?
They engineered a very rigorous, automated filtering process built on 3 non-negotiable pillars: quality, difficulty, and diversity.
Okay, let's break those down.
The quality pillar was the baseline. They removed any examples that had formatting errors, broken text, or missing images. They also ensured that the reasoning traces, the step-by-step solutions they were using as examples, were cleanly generated from a highly capable model. In this case, Google's Gemini thinking model.
Okay, so the data is clean and clearly legible. How do they handle the difficulty pillar? I'm genuinely curious about this because if you just want to find out what's hard, wouldn't you just ask the big 32 billion parameter model what it struggles with and use those questions?
You'd think so, but they were incredibly strict to avoid any flukes. They used a dual model filter. They had 2 entirely different models try to solve the questions without using any deep reasoning traces.
Interesting. 2 models.
Yeah, they used a smaller 7 billion parameter model and that larger 32 billion parameter model. If either the small model or the large model got the question right on the first try, the question was deemed too easy and thrown out entirely.
Wow. So they only kept the problems that completely stumped both AI models right out of the gate.
Exactly. By using 2 models of different sizes, they reduced the chance of an anomaly. Like a model accidentally getting an easy question wrong due to weird phrasing, or a model randomly guessing the right answer to a hard question.
That filters out a lot of noise.
It does. Furthermore, they looked at the length of the step-by-step solutions, counting the tokens. They prioritized questions that required the longest, most extensive thinking steps. The assumption being, mathematically, harder problems require more tokens of computation to resolve.
That is ruthless filtering. So the third pillar is diversity, which I assume means they didn't just want 1,000 calculus problems.
Right. They needed the model to generalize its reasoning across any topic you might throw at it. So they used an AI to classify all the remaining ultra-hard questions into specific domains based on an established mathematical subject classification system.
How many domains were we talking?
They ended up uniformly sampling across 50 different domains. We are talking everything from quantum theory and thermodynamics to biology, field theory, and number theory.
Here's where it gets really interesting, though. Did they actually need to be that obsessive? So what does this all mean for the final product? Like if they skipped the diversity step, would it really have failed?
Well, the researchers ran ablation studies, basically, deliberately removing one pillar at a time to see if the structure collapses.
And did it?
It absolutely did. If they ignored the dual model difficulty filter and diversity and just picked 1,000 random high-quality samples, performance tanked. If they picked 1,000 maximally diverse samples but didn't rigorously check for difficulty, it was equally bad.
Wow, so no cutting corners.
None. On a notoriously tough benchmark called the AME24 math test, dropping just one of those pillars caused the model's accuracy to plummet by roughly 30%. You need the perfect trinity. The data must be clean, it must span multiple disciplines, and it must be fiercely difficult.
Okay, so we have this perfectly curated 1,000 example key. They fine-tuned the model in 26 minutes for the cost of a dinner. Now the model knows how to lay out a deep reasoning trace. But here is the next huge hurdle, and this gets to the heart of test time scaling. When you and I are using an AI, how do we actually control how long it thinks? If I ask it a simple coding question, I don't want it burning expensive cloud compute power for 5 minutes.
Right. That's a waste of money.
But if I give it a complex physics problem, I want it to chew on it for a while.
Controlling that thinking duration dynamically is a surprisingly difficult problem. You can't just type into the prompt, hey, think about this for exactly 2,000 tokens.
Why not?
The paper clearly demonstrates that this token conditional control completely fails. Language models generate text one token at a time. They don't plan their word count in advance, so they're famously terrible at counting their own output. If you tell it to stop at 2,000 tokens, it will regularly blast right past that limit.
I can imagine. It's like asking someone to speak for exactly 500 words without letting them look at a word count. They're going to guess, and they'll probably be wildly wrong.
Exactly.
So what if you ask to think in structural steps, like think for 64 steps?
They attempted step conditional control as well. They told the model, you have 64 steps to solve this. And the AI immediately learned how to exploit the instructions.
Oh, of course it did.
Because the model knows it has a step constraint, it will sometimes just make a single step incredibly long, like hundreds of tokens crammed into one step to get around the limit. Or even funnier, it would count down to step 0, realize it wasn't finished solving the math problem, and just start counting into negative numbers.
Oh, wait, really?
Yeah. It would literally output -1 steps left, -2 steps left, just so it could keep its internal monologue going.
That is hilarious. It's like a toddler negotiating for more playtime before bed. -5 minutes, Mom.
Pretty much.
Okay, so asking nicely doesn't work. Telling it step limits doesn't work. How did they achieve efficient scaling? Let me see if I can try an analogy here. It sounds like they needed a strict exam proctor. If a student takes too long on a test, you don't politely ask them to wrap it up in 50 words.
No, you wait until the clock strikes 0, you walk over, you snatch the paper away, and you say, pencils down, what is your final answer right now?
Exactly.
Technically speaking, the system acts exactly like that strict proctor through a method called budget forcing. The researchers monitor the exact number of tokens the model is generating during its thinking phase in real time.
So they are watching it closely.
Yes. The very millisecond it hits the maximum token budget they've set, the system forcefully intervenes. It injects a specific end-of-thinking token delimiter directly into the model's context, followed immediately by the phrase, final answer.
Wow. So the model is violently pulled out of its internal monologue and forced to just output whatever conclusion it has reached up to that point.
This gives the user 100% perfect control over the maximum test time compute. It physically prevents the model from spinning its wheels, going off on tangents, and wasting expensive compute resources.
That's brilliant.
If you only want to pay for 1,000 tokens of compute time, you will only ever use exactly 1,000 tokens. That level of absolute unbending control is what directly translates to predictable, efficient scaling on the top end.
I love that. The proctor just yanks the paper.
Yeah.
But that solves the problem of making the model stop.
Yeah.
What about the other direction?
What do you mean?
What if we have a really hard problem and the model thinks it's done, but we know it needs to think longer to get a better answer? How do we force a minimum budget where we say, no, keep thinking, without just telling it to do so, which we know it ignores?
Right.
I mean, why not just let the model answer, and if the answer is too short, we throw it in the trash and make it guess again until it naturally gives us a really long, thorough explanation?
That's a very natural, intuitive leap. In the AI world, that method is called rejection sampling. You just reject the short answers and sample again until you get a long one.
Sounds logical.
It does, but this raises an important question, and the paper's findings here are highly counterintuitive. You would assume that artificially filtering for naturally longer generations would yield better, deeper answers. But the researchers found a severe inverse scaling trend with rejection sampling.
Inverse scaling.
Yeah. The longer they forced it to naturally generate, the worse the answers got.
Wait, really?
Yeah.
A longer thought process made it less accurate. Why?
When they looked at the actual text logs, the reason became obvious. If a model naturally generates a short, concise reasoning trace, it's usually because it understood the problem immediately, applied the correct formula, and solved it efficiently.
Right, it just knew the answer.
Exactly. But if a model generates a massive, rambling 8,000 token reasoning trace completely unprompted, it's almost always because the model is completely lost. It's going down blind alleys, realizing it made a mistake, backtracking, getting confused, and spiraling into a hallucination.
So rejection sampling is basically the AI equivalent of a student frantically erasing and rewriting their essay during the last 5 minutes of an exam.
Exactly.
It's not deep thinking. It's just pure panic. So if rejection sampling is out, How did budget forcing solve the minimum time limit?
They monitor the model's output, and when the model decides it's finished reasoning, it tries to output that end-of-thinking token.
To hand in the test.
Right. But the system simply refuses to accept it. It actively suppresses the generation of that end token. But it doesn't just leave it blank, it injects a single word into the model's internal monologue to prompt further reflection.
Just one word.
Yes. The system literally types the word wait into the model's thought process.
There was an example in the paper about this weight injection that made me laugh out loud
Yeah.
because it perfectly illustrates how these models are essentially just sophisticated autocomplete engines.
The Raspberry one.
Yes. The prompt asks the model a classic trick question. How many R's are in the word raspberry? So the model starts its internal monologue and spells it out. It finds the first R, the second R near the end.
Missing the silent one.
Exactly. It concludes there are 2 R's. It generates the text. The number of R's in raspberry is 2. And it tries to output the end token to hand in its test.
And the budget forcing system kicks in, suppresses the end token, and injects wait.
So the model's internal trace suddenly reads, the number of R's in raspberry is 2. Wait.
Right.
And because it has to continue the thought based on that newly injected text, the model literally generates, let's reread the question carefully. It then spells the word out much slower, with dashes between every letter. R-A-S-P-B-E-R-R.
And then it catches it.
It counts them again, realizes it missed the one right in the middle, and finally outputs the correct answer, 3, just by injecting, wait, they forced it to self-correct.
It's a profound insight. The researchers experimented with different words, like injecting or alternatively, but wait consistently yielded the best performance extrapolation.
That's wild. Just one word.
By just using this simple wait hack, they were able to push the model's accuracy on the ultra-hard AME24 math test from 50% all the way up to 57%.
That is a massive jump.
It is, especially without any extra training data. It works better than rejection sampling because it allows the model to reach a natural conclusion and then prompts a structured review process. It's saying, good first draft, now critique it.
Okay, so budget forcing, cutting it off, or whispering wait is highly efficient. But logic dictates that you can't just inject wait forever. You can't make it review its work 1,000 times and expect it to cure a disease.
No, absolutely not.
Eventually, you must hit a wall. How do you scale efficiency beyond the limits of a single train of thought?
You eventually hit the limit of the model's context window. You can think of the context window as the AI's short-term memory limit.
Okay.
If you suppress the end token too many times, the model thinks for so long that it literally runs out of memory to remember the beginning of its own thought process. It's like trying to hold a giant complex math equation in your head. Eventually, you drop a variable.
Yeah, that makes sense.
When that happens, the model gets stuck in repetitive loops. If you look at their data charts, the accuracy curve for sequential scaling, which is this process of one long, continuous thought, eventually flattens out entirely.
So what's the next gear? How do we break past that ceiling when single thought scaling maxes out?
If we connect this to the bigger picture, we have to transition from sequential scaling to parallel scaling.
Parallel scaling.
Instead of forcing one model to think for a very long time in a single line of thought, you run multiple instances of the model simultaneously to explore different possibilities. The simplest form of this is majority voting.
How does that work?
You ask the system to generate, say, 16 different independent reasoning paths and answers. Then you simply look at the final outputs and pick the most common answer. If 12 out of 16 independent paths arrive at the number 42, it's highly likely that's the correct answer.
That makes perfect sense. It smooths out any weird hallucinations or random math errors in a single run. But is that the most advanced way to do parallel scaling?
They went a crucial step further, using a tree search method called rebase. This is where test time scaling becomes incredibly powerful. Rebase doesn't just wait until the end of the 16 paths to vote on the final answer.
What does it do?
It uses a separate tool called a process reward model. As the main model is generating different parallel thoughts step by step, the reward model acts like an active coach. It evaluates each individual step in real time.
So it's actively managing the compute budget during the parallel paths. Let me try an analogy. Think of Rebase like a master chess coach standing over your shoulder while you consider your moves.
Okay, I like that.
You don't have to play the entire game to find out you lost. You look at a move, and the coach immediately says, that path leads to checkmate in 3 moves. Stop thinking about it. By killing the bad paths early, you don't waste time.
That captures the mechanism perfectly. If one path is clearly going down a wrong mathematical alley, The process reward model prunes it. It instantly kills that generation.
Saving that budget.
Exactly. It then redirects the system's compute power to duplicate and explore the paths that are mathematically sound. By combining sequential scaling, using way to get the model to think deeply, with parallel scaling like rebase, searching multiple verified paths simultaneously, the researchers pushed accuracies even higher without ever hitting those hard short-term memory limits.
This is absolutely mind-blowing. Okay, let me bring this all together for everyone listening because the implications for how we use technology are massive.
They really are.
What the S132B paper proves is that the narrative we've been sold, that you need billions of dollars, massive server farms, and impossibly complex reinforcement learning to achieve top-tier AI reasoning, is just fundamentally untrue.
It's a myth.
You don't need to brute force the knowledge into the model. The model already knows it. You just need 1,000 perfectly curated, incredibly difficult examples to teach it how to access that knowledge. And then you just need a strict proctor.
A very strict one.
You need a system that manages the compute budget flawlessly by forcefully stopping it when time is up, whispering, wait when it needs to double-check its work, and using a chess coach to prune the bad ideas.
It is a stunning victory for elegance and efficiency over sheer scale. It proves that intelligent test time scaling can rival the most expensive pre-training budgets on Earth.
And for you, listening to this, whether you're at your desk or commuting, what this really means is that high-level reasoning AI isn't going to be locked up in a corporate vault.
No, it's democratizing it.
Exactly. Because this methodology is so efficient, and because models like Qwen are fully open source, these kinds of elite tools will soon be able to run on incredibly small budgets, eventually right on your own local devices. The barrier to entry to build a reasoning AI just dropped to the floor.
It's going to change everything.
But it leaves me with one final kind of wild thought to mull over. We just learned that 1,000 examples were enough to unlock elite mathematical reasoning, an ability that this model already had buried deep inside its pre-training, just waiting to be activated. So it makes you wonder, what other latent superhuman abilities are currently lying dormant inside these massive open source models, just waiting for someone to find the right 1,000 example key to unlock them? Keep exploring.